The purpose of this video is to discuss a little bit about how amplifier classes behave in bipolar transistors and in junction field effect transistors. And in order to do that, if you will refer to Teach Yourself Electricity and Electronics, 5th edition, in Chapter 24, we discuss amplifier classes, Class A, Class AB, Class B, and Class C. What I've shown here are reproductions of Figure 24-3 and Figure 24-4. These show characteristic curves for a bipolar transistor on the left, that is Figure 24-3, and a junction field effect transistor on the right, that is Figure 24-4. And I have labeled the various classes of operation and where the bias points would be under no signal conditions. I sub B is the base current. I sub C is the collector current. That's in a bipolar transistor. Notice that with forward bias we get conduction. With reverse bias we don't. More or less. The forward breakover point actually for a transistor like this is about 0.6 of a volt in a silicon bipolar transistor, the same as the forward breakover voltage in a silicon diode. In a junction field effect transistor, the situation is quite a bit different. We have the gate voltage, and here we have the drain current. The gate is the analog of the base, and the drain is the analog of the collector, but although the characteristic curve is similar in shape, the bias points are different. And instead of cutoff, we call this situation pinch-off. Normally with reverse bias, we actually can get conduction in a junction field effect transistor or JFET. In order to get pinch-off, we have to apply a significant amount of reverse bias. Now remember, these curves are representative of the no signal condition. If we actually apply a signal to one of these devices, we're going to get fluctuation that goes up and down along this curve as the signal alternates, an AC input signal alternates. In the Class A case, it's always going to remain within that straight line portion of the curve here, so that the output waveform will always be a faithful reproduction of the input waveform, just bigger, hopefully, if we have an amplifier. That's represented by this slope of this curve. The steeper the slope, the greater the amplification will be in general. Now in the case of Class AB, in either of these curves, the signal in Class AB1 ventures outside of this straight line portion of the curve, but it never actually makes it to cutoff during any part of the cycle, cutoff or pinch off. So the device always conducts during 100% of the input cycle. In the case of Class AB2, however, during somewhat less than half of the cycle, but a small part of the cycle, the device is actually cut off or pinched off. So as the signal alternates, we get a situation where during somewhat less than half of the cycle, that's Class AB2, somewhat less than half of the cycle the device is cut off. One of the interesting things about all of this is that in order to get significant amplification with these Class AB amplifiers as opposed to Class A, we need to drive them harder. I've represented that by making the ellipse here, as it were, bigger and bigger. Class B operation, during half of the signal cycle the device conducts, during the other half it doesn't. So in effect, we get half-wave rectification of the input signal waveform. In order to get significant amplification, though, we have to drive the device rather hard. Now, in the case of Class C operation, the no signal bias point is actually in the cutoff zone or the pinched off zone. In order to get any output at all from the device, we need to have a significant amount of driving power, more than either of the other types of amplifiers or any of the other types. In addition, Class C operation produces significant distortion of the waveform in the output. The further we go down this curve at the bias point, the greater the amount of distortion we will see in the output waveform. So, in fact, if we were not to drive this device sufficiently, we wouldn't get any output at all in Class C operation. So those are the basic characteristics of Class A, Class AB1 and AB2, Class B, and Class C amplifier operation. Now keep in mind that the only true waveform linear amplifier is going to be the Class A amplifier, because in order to get a truly linear reproduction of the input signal waveform, we have to stay within that straight line part of the curve. However, when it comes to the modulation envelope on a radio frequency signal, we can get away with Class AB operation and we'll still get a linear reproduction of the modulation envelope. Even with Class B, we'll get a linear reproduction of an amplitude modulation envelope in a radio frequency power amplifier. But when we go into Class C, we can't get a linear reproduction of the modulation envelope, and so the modulation will become distorted. Class C operation for a power amplifier, therefore, is used primarily in radio frequency applications where we have frequency or phase modulation, in which case the amplitude of the signal doesn't change, or continuous wave operation, also known as Morse code or on-off keying, in which the signal is either full on or full off. Frequency shift and phase shift keying will also work with Class C, but AM, old-fashioned amplitude modulation, you don't want to use Class C as a radio frequency power amplifier for that particular mode, nor single sideband. You don't want to use a Class C amplifier in an attempt to make a power amplifier work for single sideband. So that's basically the situation here with classes A, AB1, AB2, B, and C, in particular in regards to radio frequency power amplifiers.